What does it mean for an algorithm to have O(n) time and space complexity, and why does it matter? The big O notation seems somewhat abstract and complicated at first, especially if you look at its mathematical definition without first building a proper intuition for it. So in this video, we will do exactly that. We'll first try and understand the intuition behind big O, what it means, and why it matters, and later even dabble a little in the more rigorous mathematical definition of big O. First, a very quick look at why big O matters, and why it's ubiquitous, especially in the studies of algorithms. In this example, we will look at big O in connection to time. On the x-axis we have problem size, and on the y-axis we have time in seconds. What exactly this means is not important right now. The important part is to build an intuition on what it means when big O is bigger or smaller. As you can see, this is a linear function. The line is straight and increases linearly with problem size. This is what you'd normally think of when you talk about a O(n) algorithm. Now I will show you the same problem but with an algorithm that takes O(n)² time. As you can see, there is a time explosion when the problem size increases. This will make it infeasible to do whatever calculations we're trying to do here when the problem size increases. This is why algorithms and similar problems are almost always discussed in terms of big O. It's not perfect, and we'll see later why, but it gives a very quick and simple way of understanding the runtime and other complexities of an algorithm. Now let's try and understand big O intuitively by the help of a simple example. Let's take an unordered list of numbers of length n. That is our problem size. Now let's pretend we'd have to create an algorithm that has to check just once if a specific number is in this list. Now pause the video and try and think of a simple algorithm to check if a specific number is in this list. It does not have to be code, just a simple recipe that you can follow in your head step by step and always get the right solution. It helps to create a small concrete example with concrete numbers. Alright, let's look at a simple example. Let n be 5 and the actual list be 15379, and the number we're searching for shall be 7. A simple algorithm would be to just look at each number in the list and see if it's equal to the number 7. If it is, we say the list contains the number 7. If not, and we've checked all numbers, we can safely say the number 7 is not in this list. This is obviously a correct algorithm for this problem. If you had a similar or the same algorithm in mind, then you already have a basic grasp of big O. This algorithm has a time complexity of O(n). This stems from the condition in the algorithm that if the number is not part of the list, we have to check at least all numbers in the list, which by our definition has length n. Thus, in the worst case, we have to check at least n numbers, giving us a time complexity of O(n), linear in problem size. So you could say that big O in this example is a function of cost. Here it will be a function of runtime, so the time needed to run the algorithm on average, for example in seconds, assuming checking each number takes 1 second. Little side note for programmers: when looking at code or pseudocode, the easiest first guess for runtime is always to look at the amount of nested loops. Here we have one loop, and thus an easy first guess would always be O(n). If we had two nested loops, the first guess should be O(n)². This is not always straightforward and sometimes needs more attention to detail, but it usually is a good first guess. Now back to our example. In this case, our simple algorithm actually has the best possible runtime. You cannot determine if a number is not part of this list without at least checking the entire list. If, for example, the number we're searching for would be the number 9 and you'd only check the first 4 numbers of this list, you'd falsely say that the number is not part of the list, even though it obviously is. In the studies of algorithms, we'd say that this problem has a lower bound of omega n. This is not part of this video and slightly more advanced, and thus will not discuss further, but left for you to read up on if you're interested. But with this information, you can safely say that if someone came to you and said he has an algorithm for this problem with runtime O(n², you'll know that it is not optimal and can immediately gauge the quality and speed of his algorithm. Now, for further and deeper discussion of Big O, I find it essential to look at the mathematical definition. Now, don't get intimidated, it might look complicated at first, but once it's laid out in common terms, it's actually very easy to understand. Define a cost function f that goes from the natural numbers to the positive real numbers. Now we define O as a set of functions that do not grow quicker than f. So here you can see the definition of this set. We have all functions g that go from the natural numbers to the positive real numbers, with the condition that there exists c bigger than 0 and n0 that is an element of the natural numbers such that g of n is smaller than c times f of n for all n bigger equal than n0. Now this might sound difficult at first, but let's try and put this into simple terms, and I promise it will make sense. This means that f is an asymptotic upper bound of g. This can be seen in this graph. Let's plot some arbitrary function g that is in some O of f. Let's plot this f at first below of g. Now there exists some constant c that pushes our function f above the function g for all n past n0. This is what it means to have an asymptotic upper bound. After some threshold n0, it will always be above or equal g, and it will never be smaller. Let's do another example. The function 2 of n is an element of O(n². Because when we start to plug in some numbers, we can see that with c equals 2 and n0 equals 1, the function n² will always be above the function 2n. This example now illustrates the problem with big O notation and why it's not the only and absolute measurement of runtime. The function 2n is an element of O of n. We can just set c to 2 or 3 or whatever integer above 2 and it will be an effective upper bound. This means in big O notation, constant factors are negligible and are thus often removed from final runtime analysis. So an algorithm that technically has runtime of O 10,000 times n can be written as having runtime O of n, as 10,000 is just a constant factor. This obviously starts to skew this very intuitive and simple understanding of O related to time cost by this hidden constant factor. These constant factors can be so huge that in some special cases an algorithm with runtime O(n²) can beat algorithms with reported O(n) runtime, especially on real hardware with real constraints. This definition also allows us to not only throw away constant factors, but even functions of n of smaller magnitude. Thus, O(n² plus n to the power of 1.9 can be written as O(n² and be perfectly mathematically correct. So in conclusion, Big O is a very useful tool to quickly describe the time cost of an algorithm. It allows for very simple comparisons between algorithms that solve the same problem but have vastly different runtimes. But it is absolutely vital to understand the mathematical definition and pitfalls that can happen in Big O notation, and to not always blindly trust every Big O analysis. Thank you for watching my first video on this channel, and I hope you enjoyed it. If you did, make sure to leave a like and maybe even subscribe, it would greatly help me out. If you didn't, please tell me in the comments and I will try and improve for the next video. There will probably be some interesting algorithmic problem or some more vital theory needed to understand deeper problems. I'm Argonaut, you've been watching Argonaut Developments, and I'll catch you on the next video.